Okay, welcome back. Today we're going to talk about the Ricci flow on compact manifolds that have positive curvature and are not too far away from the sphere in a certain sense, and prove a theorem that if we are that close to the geometry of a sphere, then in fact the metric solving Ricci flow will converge to a metric of constant curvature. So consider a compact smooth Riemannian manifold Mn with initial metric G0 as before, and recall that the Riemann tensor can be decomposed into three orthogonal parts, and this is the part that contains the scalar curvature, and this is the part that contains the trace-free Ricci tensor, and this is the part which is called the Weil tensor, and this is completely trace-free. And what I mean by being close to a constant curvature metric is that the second and the third part here are small compared to the first part, which is the scalar curvature part. And the theorem then goes as follows. Theorem. So suppose Mn G0 with dimension n greater or equal than 3 is smooth, compact as above, with positive scalar curvature. And suppose that the solution of Ricci flow, G of t of ddt G equals minus 2 times Ricci of G, satisfies for some 0 less than delta less than 1 and some c 0 less than infinity, the inequality that the traceless Ricci part together with the Weil part of the Riemann tensor are bounded by C0 times the scalar curvature to the 2 minus delta for all pt in Mn cross time. Then, so if we have this smallness condition happening on the whole flow, then the solution Gij tilde t of the normalized equation where I take ddt of g tilde ij is equal to minus 2 the tilde Ricci curvature of the tilde metric, and then here's the normalizing term plus 2 over n times little r tilde g tilde ij, where little r tilde is the average of the scalar curvature over the manifold with initial data g tilde 0 is the same as before, then the solution of this rescaled equation will converge to a constant curvature metric. So smoothly will converge in C infinity to a smooth metric g tilde infinity which has constant sectional curvature. And such a space of positive constant sectional curvature is called a spherical space form. That's the theorem. And a couple of remarks are in order. So the first remark is that this is a useful theorem only if we can find conditions on the initial metric that allow us to prove that this condition, the main assumption of the theorem, is in fact true for all time. So the theorem is useful only if the so-called pinching condition u plus v squared, v squared plus w squared less than constant times r to the 2 minus delta is true under natural assumptions. On G naught. You want to make assumptions only on the initial metric, not on the whole flow. So this theorem is a result that says in all those cases where you manage to prove from the initial conditions that later on such a pinching condition must hold, then you can apply the theorem. And the pinching condition here is useful, can be interpreted in the following sense. Why is it such a natural condition? Well, the condition is called pinching because when you rescale in such a way that you rewrite the inequality such that you have a scaling invariant quantity on the left-hand side, then on the right-hand side you end up with r to the minus delta, so some small negative power, and this of course tends to infinity, tends to 0 if the scalar curvature r tends to infinity. And in particular, near a singularity, we will see that the scalar curvature has to tend to infinity. Remember, we showed that if a singularity at the end of the maximal time interval, the curvature will blow up. So if the curvature blows up, then this pinching estimate makes sure that the trace-free component of the Riemann tensor tends to 0, so only the U part, the first part containing the scalar curvature, is left. And this is what we want. We want to have in the limit a metric of constant scalar curvature. And notice also that, of course, this only makes sense for n greater or equal than 3. Recall that for n greater than equal to 3, if V and W are both 0, then we had shown from the Bianchi identity that then the scalar curvature has to be constant. So, whereas this condition, of course, for the two-dimensional case is vacuous, it doesn't have any content. Another remark I would like to make concerning the rescaled equation, we will see that the solution of the rescaled equation is related to the solution of the original Ricci flow, but just by multiplying with a constant factor dependent on time. And the rescaling is chosen in such a way as to keep the volume constant. So note that if ddt of the metric is equal to minus 2 times Ricci tensor plus 2 over n times the scalar curvature times the average of the scalar curvature times g tilde ij, that then the time derivative of the induced volume element with the usual computation of the determinant of a matrix, you end up with 1/2 of the trace of the right-hand side. So this would be minus the scalar curvature, the trace of the Ricci tensor, and then the trace of this one here is n times 1 over n. So this is minus plus r tilde times d mu tilde, which means that ddt of the volume of the g tilde metric is just minus the integral of the scalar curvature d mu tilde plus the average in integral of the scalar curvature, and of course this is exactly 0. So the choice of this term here is done exactly to make sure that the volume is constant. We will see that later also. And finally, the last comment is that, of course, these space forms of positive curvature, the spherical space forms, are all classified. So spherical space forms are classified. They are all quotients of the standard sphere by groups of isometries. Any space form Mn G is a quotient of the sphere of Sn by a discrete group of isometries acting freely on Sn. And examples are, for example, in dimension 3. These are, of course, RP3, where the group is just Z2. And you have the antipodal map, but there's also the length spaces with 2 parameters. These are isometries that come in a natural way from R4, if you embed S3 into R4. So they are all known, and the classification, of course, means you have to classify the possible groups that act on S3. So this theorem says if you manage to find initial conditions on the metric that make this pinching condition true, then you get convergence to a spherical space form. And since we've seen along our flow, it's completely smooth, so we have diffeomorphism of the initial manifold to the later one. It means that we get a complete classification of the initial manifold if we can make sure the pinching condition is true later on. This will be done later in a separate class to look at possible pinching conditions. Now we concentrate on proving this general theorem and then focus on the possible pinching conditions later. Now the key point is to prove that the pinching condition, if it happens at one point, we know we get sort of the right behavior, but it's not enough to know that this happens at one point of the manifold. We really have to show that if the curvature gets big, and near the singularity, it has to be big at some point, then it is big in a sufficiently large neighborhood so that we can conclude the whole manifold has the curvature close to the curvature of a sphere everywhere. I should say that the strategy of this proof goes back to Richard Hamilton's original paper, which I've put onto the web for you. There's a proof strategy due to Richard Hamilton in his 1982 paper. And the first step we want to do is now, assuming this pinching condition, to prove that we get gradient estimate on the scalar curvature, which allows us then to argue that if the curvature is big somewhere, it has to be big in a whole neighborhood, and therefore we have to have this pinching in the whole neighborhood. And here goes the gradient estimate. The theorem. Gradient estimate under the assumption of the pinching estimate. And it says that if G solves Ricci flow with R greater 0 and v squared plus w squared less than the constant times r to the 2 minus delta holds, then for all eta greater than 0, I can find a constant c of eta, which is a constant that depends in particular on the initial data and on the constants appearing in the pinching estimate, such that the gradient of the scalar curvature at any point in space and time satisfies an estimate like this, eta times scalar curvature to the 3/2 plus this constant c of eta. Notice that this estimate is not quite breaking the scaling, because you see here the point is that on the right hand side the scaling is slightly better than 1 on distance squared, and that gives us this scaling invariant knowledge about the behavior of the curvature. But here r to the 3/2 scales exactly like the gradient of the scalar curvature. The improvement that's here, and therefore almost scale breaking, is that this eta can be arbitrarily small, and this constant c of eta is a fixed constant which does not change if r goes very large. So the break in the scaling, the improved estimate here is the fact that eta can be arbitrarily small. Now, the proof of the gradient estimate of course has to work with the evolution equation. So in the first step for the proof of the gradient estimate, we have to compute the time derivative of the gradient of the scalar curvature. We compute ddt of the gradient squared of the scalar curvature. So this is ddt of g upper ij of gradient ir gradient jr. And then from ddt of the inverse metric, we get a term which is 2 times the Ricci curvature times gradient AR gradient JR. And then from here we get 2 times the Gij times the gradient of Laplace R times gradient JR, because it's symmetric in I and J. And then there was another term in the evolution equation of the scalar curvature, which gives 2 Gij times gradient I, and here this term was the extra term in the evolution equation of the scalar curvature was like this. Since ddt of r, remember we computed that this was Laplacian of r plus 2 times the Ricci curvature split. Okay, so we get this identity, and now use the fact that we can commute the gradient of the Laplacian with the Laplacian of the gradient. So gradient I Laplace R is equal to the Laplacian of gradient IR. This was something I did in the first or second lecture, I remember, plus the commutator in this case was the Ricci curvature times gradient JR. So inserting this, we can then exchange here the Laplacian of gradient IR. But this is the same as the Laplacian of the Ricci of the gradient of R squared, with a mistake, which is exactly minus 2 times the Hessian of r squared. So this term here replaced with this, and then the error I made here is plus 2 times plus 4 times 4 2 times 4 times 2 is 4 times the Ricci curvature times the gradient I of r, gradient j of r, coming from here. And then from here I have another 2 of those. So I have altogether, I have 6. And then here I have some terms which look like plus 4 times gradient I of Ricci squared times gradient I r. Okay? Now, the important point here is the structure. So, this here, this there. This is curvature times gradient of scalar curvature squared. And here we have gradient of curvature times gradient of curvature. Now, in view of the pinching condition, all the curvatures are comparable to the scalar curvature. So we can just brutally estimate this by Laplacian of gradient r squared minus the Bochner term, the Hessian of r squared, and then we just combine all the bad terms here, the constant depending on just the dimension times the scalar curvature times the gradient of the Ricci tensor squared. Notice that, of course, the gradient of the Ricci tensor squared, since r is the trace, is bigger than 1 over n times the gradient of the scalar curvature squared. So we can just combine also these terms involving the scalar curvature just into one big term involving the gradient of the Ricci tensor squared. And again, I used here, this term here includes, of course, the scalar curvature, and it includes the trace-free Ricci, but the trace-free Ricci, by our pinching assumption, is definitely bounded by the scalar curvature times some multiple depending on n. So we get this inequality here, and just to make sure I have it all on one board, I write this into this box. Okay. So we have an upper bound. So this is a good term if you think of the maximum principle. This is also a good term, but this term is very bad because it is in the same order of gradient Ricci, but it's not just involving the scalar curvature, it's involving the full gradient of the Ricci tensor, and it has an extra factor, which is the scalar curvature, which we know can go to infinity. So we can definitely not easily get a gradient bound from here. Now the idea is, of course, to exploit the pinching condition and remember that in a previous lecture we had this trick of adding a lower order term to the term we want to estimate. So the lower order term is now going to be a curvature term. We're going to add a suitable multiple of a curvature term in order to deal with the bad gradient term, Ricci on the right hand side. And what kind of curvature term should we use? Well, the idea is to create a suitable Bochner term from the trace-free part of the Ricci tensor. So now consider the trace-free Ricci tensor. Remember, this was Ricci minus 1 on n times r times the metric, and such that the norm of the trace-free Ricci tensor is equal to the Ricci tensor squared minus 1 on n r squared. Let's call this function f for a moment. So let's just compute now ddt of f. ddt of f has to be computed from the evolution equation for the Ricci curvature, and we did that in the course where I computed all these evolution equations. And what we proved was ddt of Ricci was Laplacian of Ricci, and then there was a term involving the full Riemann tensor, Ripjq, and this was contracted with the Ricci tensor. And then there was a term which was the square of the Ricci tensor. This was the evolution equation of Ricci. So now we can, from this and the evolution equation of the scalar curvature, compute the evolution equation of f. So we get ddt of f is equal to now ddt of Ricci squared. This is ddt of, let me be slow, this is gi j g k l of r I k r j l. And so I have to not forget these terms. So this is the inverse of the metric. It's symmetric, so I get from here plus 4 times the Ricci tensor, say Rij g k l r I k r j l. This comes from these 2 terms here. And then similarly here I get, because of symmetries, twice let me write it like R Ij times Laplacian of R Ij plus 2R I p cubed I pj cubed R p cubed, and minus 2 R I k R k j. And now I forgot, of course, minus, sorry, from here. This is just the evolution equation of Ricci squared. It's just part of it, it's not f yet. This is just this. And now, here we can again convert this into the Laplacian of Ricci squared minus the error, and the error is exactly the gradient of Ricci squared, so this takes care of this term. And now notice that this term here, Rij times the square of Ricci, is just a trace of the cube of the Ricci tensor, which is exactly the same as this term here, and this cancels. The 4 from here cancels with the 4 from there. So this term here goes completely away. So you just get one extra term, 4 times Ripjq times Rij times Rpq. Well, that's the formula for the evolution equation of the Ricci tensor squared. So and now, using our evolution equation for R, notice that ddt of R squared then is of course Laplacian R squared minus 2 gradient R squared plus 4 times R times Ricci squared in view of the evolution equation of the scalar curvature. So if we now put it together, we get the evolution equation for f. ddt of f is equal to the Laplacian of f. And then we get minus twice gradient Ricci squared minus 1 on n gradient scalar curvature squared, taking care of this term, this term, this term, and this term. And then the absolute terms combine in such a way that I have 4 times R, I, P, J, Q times R, I, J. And this term here with is exactly, when you take this out, this is exactly what happens if you take in the RPQ terms here, if you decompose this into the trace-free part, R0PQ, what you have left is 1 over n times R times the trace in P and Q. But this is exactly 4 over n times Ricci squared times scalar curvature. And 4 over n is exactly what we get there with the other sign, because we have a minus here. So I can just combine these two terms and produce the scalar curvature free part of the Ricci tensor in the second factor. So it's really important to look at this absolute term. Notice that this here is a good term because the matrix squared is always bigger than 1 over n times the trace squared. So this is certainly greater or equal to 0. We will see that it's even better. But this is a bad term and we have to see how we can estimate it. Now notice that if this decomposition worked out so well for this one, let's also do decompose the Rij. So we can write Ripjq times Rij times R0PQ. We can write this as Ripjq times the trace-free part, Rij times R0PQ, plus 1 over n times the scalar curvature. Now I have to take the Ij trace of this, but the Ij trace of this is just this Ricci curvature PQ term, multiplied with the trace-free part of the Ricci tensor. But now trace-free multiplied with the full tensor is the same as, if I now decompose this guy, it will have the trace part, but the trace part times this is 0. So in this product, only the trace-free part survives, so I can put a 0 here without making any mistake. Now, the point is, what is contained in these terms? Well, in the Ricci, in the Riemann tensor, we have the W term and the traces Ricci and the scalar curvature term. So now this can be estimated if I take absolute values brutally. I can obviously estimate these terms by something, some constant depending on n, times the scalar curvature part times the traceless Ricci part. There will be another term which involves the W part times the traceless Ricci part squared. And there will be another term involving the traceless Ricci part to the power 3, because this also contains some traceless Ricci part. And this last term here clearly just contains scalar curvature times traceless Ricci part. So I can estimate all these terms in this way. And each of these terms has at least two factors which are estimated by our pinching condition. So the whole thing here can be estimated by some constant C1 times R to the 3 minus delta by assumption. This is a very crucial point in this evolution. You should expect this, right? Because you are computing ddt of the trace-free part, so the right-hand side, the absolute term on the right-hand side, should have some factors involving the trace-free part. It's crucial here, however, that we actually demonstrate that this is true and that the constant is just depending on n. Okay, so now we have, so we can write ddtf is less than Laplacian of f minus this term here, gradient Ricci squared minus 1 on n, gradient r squared. And we only pay with a bad term which depends on our assumption and on n times r to the 3 minus delta. Which is a good thing here. The idea is that this is a lower order term because of the delta. So that's where we're making use of our assumption. In terms of the scaling, this is lower order compared to this. Now this lower order term would not suffice because we have to make some use of this term here and have to use the fact that this is not just greater or equal to 0. So that's now the next lemma to show that this term here, in fact, gives us an extra good term that we want to use in order to estimate the gradient. I think we can still fit this in before the break. So, lemma. Now this is a purely algebraic lemma which could be useful in other situations, not just for Ricci flow. So for all n, we have the estimate that the gradient of the Ricci tensor squared can be estimated from below by 3n minus 2 divided by 2 times n minus 1 times n plus 2 times the gradient of the scalar curvature squared. And this number is bigger than 1 on n. So in particular, the gradient of the Ricci tensor squared minus 1 on n gradient r squared, which is the term, the good term in our computation, is bigger than n minus 2 squared divided by 3 n squared minus 2n times gradient of Ricci squared. let's call this delta n times gradient of Ricci squared, with delta n bigger than 0 if n is greater or equal than 3. This, of course, is vacuous if n equals 2, and that's why the whole proof of Richard Hamilton doesn't work for n equals 2. There's, as I said already, the assumption is empty, but also this trick, this trick here, this lemma is not giving us anything extra, and the reason is, of course, that in 2 dimensions there is just one curvature quantity, which is the Gaussian curvature. So it's just a scalar thing, and the left, these two terms in 2 dimensions are exactly the same. Now, why do you get here an estimate which is bigger than 1 on n? The reason is that this is a tensor with 3 indices, so there are 3 different traces that you can take. If you just have this tensor with just one possible trace and you forget about the gradient, then 1 on n is the best constant you can do. But since there are more traces than just a trace over the last 2 indices, you get a better constant than the 1 over n. And this technically is done by decomposing this tensor into its irreducible components. And we know that the irreducible components are given by either looking at symmetries or looking at traces. Here it's enough to look at the traces. So we define a tensor which contains all the traces. Now, I could compute it for you, but I just give you the result. You should take the tensor Eijk in the following way. Notice here that the traces of this tensor all involve just the scalar curvature, right? If you take the trace of the last 2 indices, you get gradient I of the scalar curvature. And if you take the trace of the first 2, or of the first and the third, then we get the trace again involving the scalar curvature because of the second contracted Bianchi identity. So we use Eijk is equal to n minus 2 divided by 2 times n minus 1 times n plus 2 times g ik gradient jr plus g ij gradient kr. So this is because it's symmetric and j and k, we can use the same coefficient for both these terms, but the other coefficient has to be different, so we take n divided by n minus 1 times n plus 2 times gjk times gradient ir. And now you just check that if we take the trace of Eijk, say over the first 2 indices, you just do it and you see you get exactly 1/2 the gradient of k of r. Similarly, taking the trace over I and k, you get 1/2 the gradient of j of r. And finally, taking the trace over j and k of Eijk, we get exactly the gradient I of r, factor 1. In other words, the traces of E are exactly the traces of gradient I, R, J, K. And this means that the tensor Fijk, which is the remainder, when you subtract this trace part, this thing must be completely trace-free. So f is trace-free. Now, this means, on the other hand, if you multiply f with e, so if you take fijk times eijk, you must get 0. Because this tensor, all these components involve a trace. So multiplying e with f means taking some trace of f, but we've done it such that there is no such trace, so e is orthogonal to f. So we have an orthogonal decomposition of gradient Ricci. But this means we can estimate gradient Ricci from below by one of its parts, and this is exactly I estimated from below by e squared. And now this is just a computation. Now you just compute e squared, and what you get is exactly the number I proposed up there, 3 over n minus 2 times 2n minus 1 divided by 2n minus 1 times n plus 2 times gradient r squared. And that proves the lemma. Okay. So the thing to remember is always decompose a more complicated tensor into its irreducible component, then you get better estimates than the obvious ones. This has, of course, an analogy in the gradient of the second fundamental form, where instead of the second contracted Bianchi identity, you use the Codazzi equations. So comment. Similarly, for n greater or equal than 2, there exists a delta n tilde greater than 0, such that the gradient of the second fundamental form squared minus 1 over n times the gradient of the mean curvature squared is bigger than delta n tilde times the gradient of the second fundamental form squared. Because you have the Codazzi equations that tell you that there is more than one trace leading to the gradient of h than in this case. And here you can do the computation yourself. The hint is that in this case, eijk would be 1 over n minus 2. Well, I don't remember it actually. I don't remember it. It's a good exercise. Right. So we have now this extra good term that we can use to estimate to estimate our gradient, and this we will do after the break.